Hello and welcome to this lecture. As introduced in the previous lecture, we are going to study about the fundamentals of VLSI IC manufacturing techniques, and the first unit is crystal growth and wafer preparation. And today we are going to just see the basic fundamentals, that how the basic of the IC design is the actually studying about the silicon and its properties, and then we will later find out that how silicon is actually going to be prepared and going to be the fundamental unit of any IC. Okay. I always used to tell one story to my B.Tech students about the growth of the electronics. So in brief, I am just sharing this with you people also. The growth of the electronics actually started with the invention of the electron. Before electron, the charge carriers were considered to be positive in nature. But after the invention of the electron through the cathode ray tube experiment, J.J. Thomson actually discovered that electrons are the negative charge particles. Okay, and from there onwards, the journey of electronics has completely changed. The first important device in case of the electron device, which we actually call, was the first solid state device, was the vacuum tubes. And then later on vacuum triodes were there, then diodes were there, then finally in 1947, 23rd December 1947, the invention of bipolar junction transistor completely changed the story of the development of electronics. And slowly, as you know, that BJT is a current control device, yes, it is a current control device. Then afterwards, MOS was invented, metal oxide semiconductor was invented, which is nothing but the voltage control device. And then the journey of NMOS and then PMOS and then mixture of NMOS, PMOS as the CMOS started. Yeah, so we are in the process of learning the complementary metal oxide semiconductor journey. VLSI is all about integrating as number of transistors as possible in a fixed die area or in a fixed chip area. So the subject is dedicated to how we are actually going to get the final IC packaging, right from the starting of studying the properties of silicon and how it is going to be converted in the final package of IC that we generally see in our day-to-day lives. Okay, so again I am telling you, this subject is totally a theoretical subject. No numerical is going to be asked. It is a pure story of the generation of silicon and then the properties of silicon, to wafer preparation, to oxidation, to epitaxy, then the etching process, and finally the packaging. So this is a story we actually have to study about the journey of IC manufacturing. Okay, so first chapter of this story is crystal growth and wafer preparation that we are going to study. So introduction is silicon, naturally occurring in the form of silica and silicettes, is the most important semiconductor for the electronics industry. And at present, silicon based devices constitute over 98% of the semiconductor devices sold worldwide. Okay, silicon is one of the most studied elements in the periodic table, and here it is quoted that 25,000 references have been given to the silicon and the study of the silicon. Silicon is also a commercially important element of several other important major industries such as glass and gemstones. The commercial value of silicon derives in the part from the utility of the mineral forms, which is the way silicon occurs in nature and from its abundance. And this is the reason The abundance of the silicon is the reason that why it is used most widely as a semiconductor over the other reasons as well. But the most important reason is the abundance of the silicon. Silica is integral to the manufacture of glass and related products, while certain silicates are highly valued as semi-precious gemstones such as garnet, zircon, and jade. By weight, it comprises 25% of Earth's crust and is second only to oxygen in abundance. So after oxygen, which is most widely abundance, or which is most widely, you know, found element, is the silicon. So although silicon is generally synonymous with the solid state era of electronics, as in the use of the term silicon chip, its mineral form were used in vacuum tube electronics. So what is the basic of vacuum tube electronics? I just told you just a while before. It was the silicon actually, and in the form of the silica. Silica means, you know what is silica. Silica is nothing but sand. Then the purest form is silica, and then it developed to the silicon. Mica, a silicate, found application in insulator and capacitor dielectric. Quartz, another silicate, was and still is used in frequency determining element and in passive filter applications. You might have heard about quartz crystal in case of analog electronics. The advent of solid state electronics dates from the invention of the bipolar junction transistor. I told you just a while ago, by Bardeen, Breton, and Shockley. The technology progressed during the early 1950s, exactly in the 1947, using germanium as the semiconductor material. However, germanium proved unsuitable in certain applications because of its propensity to exhibit high junction leakage currents. These currents result from germanium's relatively uh, narrow band gap of 0.66 electron volt. For this reason, silicon, which is having the 1.1 electron volt as the band gap, became a practical substitute of the germanium element or the germanium material. Okay, and silicon devices can operate up to 150 degree Celsius versus 100 degree Celsius of germanium. This is the second reason. So abundance was the first reason. Second reason was the uh, temperature. Third reason was the band gap. So all these reasons showed the properties of electron to be on higher side as compared to the germanium. Okay. So in retrospect, other reasons could have ultimately led to the same material substitution. Planar processing technology derives its success from the high quality of thermally grown silicon dioxide. Germanium oxide is water soluble and unsuited for device applications. The intrinsic, which is undoped, resistivity of germanium is 47 ohm per centimeter, which would have preluded the fabrication of rectifying devices with high breakdown voltages. In contrast, the intrinsic resistivity of silicon is about 2,30,000 ohm centimeter. Thus, high voltage rectifying devices and certain infrared sensing devices are practical with silicon. Okay, this is the other reason in comparison with the germanium, that why we prefer silicon for our construction. Finally, there is an economic consideration. Electronic grade germanium costs 10 times as much as silicon. Remember always, as a VLSI engineer, it is very important that you should remember three things. First is, when you are constructing an IC, the first important parameter is it should consume less power as possible. Second important parameter is the speed must be high. But third and most important parameter is it has to be economical. You have to compete in the real world. And how you can compete in the real world? To make your device as cheap as possible. Because if you are manufacturing the dearer devices, then nobody, the expensive devices, then nobody will take that devices. So what scientists try to compensate, to to just address this trade-off between the economic between the expense and the utilization or the application of the electronics. Okay, so similar problem impeded the widespread use of the compound semiconductors. For example, if it is difficult to grow a high quality oxide on gallium arsenide. One element oxidizes more readily than the other, leaving a metallic phase at the interface. Such material is difficult to dope and obtain in large diameters with high crystal perfections. In fact, the technology of group 3 to group 5 compounds has advanced partially because of the partly because of the advances in silicon technology. Okay, so the next topic is electronic grade silicon. Electronic grade silicon EGS, a polycrystalline material of high purity, is the raw material of the preparation of single crystal silicon. So we are going to study how crystal growth is happened. So first important thing is the electronic grade silicon, which is nothing but a polycrystalline material, which is the highest form of the purity of the silicon. EGS is undoubtedly one of the purest materials routinely available. The major impurities of interest are boron, carbon, and residues of residual donors. Pure EGS generally requires that doping elements be in the part per billion ppb range and carbon be less than 2 parts per million ppm. These properties are usually evaluated one test ignored and GOTS rather than measuring on the material itself. So depending upon the application, we are going to create the doping levels. So in case of the carbon, if I dope the carbon with the silicon, then it has to be 2 parts per million. If I dope the boron, then it has to be parts per billion. So our application will decide that how much band gap we want in case of the silicon, and then we actually manufacture that particular kind of IC. In the case of the doping elements, ppb parts per billion levels are below the capabilities of most laboratory methods, so the doping level is inferred from resistivity measurements on the test and got. To obtain EGS requires a multi-step process. First, metallurgical grade silicon is produced in a submerged electrode arc furnace as shown in figure. And let me show this figure to you so that you can better understand. This is the furnace. This is the furnace where the grading is produced. Here is the submerged electrode, and here you can see this is condensed silicon oxide, and this is some chemical reactions are here. And we need not to remember this chemical reaction, it's just for the demonstration purpose. And you will only remember what the theory we are studying behind this journey of silicon EGS, I mean electronic grade silicon generation. Okay, so first is metallurgical grade silicon is produced in submerged electrode as arc furnace as shown in figure 1. The furnace is charged with uh, quatrace, a relatively pure form of silicon dioxide, and carbon in the form of coal, coke, and wood chips. In the furnace, a number of reactions take place. The overall reacting being the solid. This is the solid silica and the solid silicon dioxide. It will be giving the solid as well as gas as well as the carbon monoxide. The process is power intensive, requiring 13 kilowatt per kg, and metallurgical grade silicon is drawn off at purity of 98%. Okay, so this is the table which shows the typical purity of the various materials used in arc furnace. The MGS used in the making of metal alloys is not sufficiently pure to use in the manufacture of solid state devices. Okay, the next process step is to mechanically pulverize the silicon and react it with anhydrous hydrogen chloride to form trichlorosilane SiSCl3. The formula is according to the reaction. So this is the chemical reaction, which is the next process to understand about the metallurgical grade silicon. And this is the actually the list. I mean, if you are impuring, this is the list of the impurity. So what kind of silica you are going to produce? The will it be quartzite, or will it be carbon, or it is MGS, or it is the EGS, or it is crucible quartz? So depending upon the type of the silica you are going to be produced, and depending upon the impurity, how much impurity you actually are going to insert inside that. This table tells you. Okay, So do not remember the whole idea of the table, just remember 1 2 points, uh, basically about the EGS. Like if you are actually actually getting the impurity of the boron, then it has to be less than 1 ppb, parts per billion. If you are mixing the gold, then it has to be 0.07 ppb. Just like 2 3 values you can remember just for the idea. Okay, nothing else. This is the last image we are going to study in today's lecture. So the earlier page where we left the formula or the chemical reaction, this reaction takes place in the fluidized bed of the nominal at a nominal temperature of 300 degrees centigrade using a catalyst. Here silicon tetrachloride and the chlorides of impurities are formed. At this point the purification process occurs. Trichlorosilicon silane is a liquid of room temperature. Boiling point is 32 degrees centigrade, as are many of the unwanted chlorides. Hence, purification is done by fractional distillation. EGS is prepared from purified silicon dichloride in a silicon trichloride in a chemical vapor deposition. So chemical vapor deposition is a process we are going to study about this chemical vapor deposition. This is the complete story. Altogether we will be studying in chapter 2 as written over here also. The chemical reaction in the hydrogen is a hydrogen reduction of trichlorosilane, and how this hydrogen is going to be disappear by forming a gas combination of HCl. Okay, this reaction is conducted in the type of system shown in figure 2. This is the figure 2. We will take a look at the end. A resistance heated rod of silica called a slim rod serves as the nucleation point for the deposition of the silicon. A complete process cycle takes many hours, and the results in the rods of EGS, which are polycrystalline in structure up to 20 centimeter in diameter and several meters in length. EGS can be cut from these rods as single chunks or crushed into a nudged geometrics as shown in the figure 3. This is figure 3, this kind of crushed thing, and here you can see the process. Well, we are going to study in detail, but here you can just have the brief idea. This is the reaction chamber, this is the silicon bridge, this is the slim rod of 4 mm diameter, this is the polycrystalline silicon rod, this is the quartz bell graphene holder, and here is the power input, this is the insulation, and inside this EGS is going to be produced and a whole chemical reaction happens. Okay, and this is the output, one form of the output you are watching. EGS in chunk from loaded into a quartz crucible, and this is the polysilicon furnace tube. Actual idea of the furnace tube, inside this EGS is produced actually, and this is the wafer rack, sorry, where this graded silicon is hold. So this CVD process is also used to grow tubes of EGS on carbon mandrels. These tubes are of high purity and strength and are used as furnace tubes in place of quartz in high temperature operations. The tubes are also sectioned and machined in form of the pedals and wafer carriers for same high temperature operations. This is the figure for that. In these applications, silicon competes with quartz and silicon carbide. The choice of silicon as a material for furnace use is advantageous because of its purity and strength. And silicon process tubes show no sagging or similar deformation after several years used in a furnace process where they are repetitively cycled between 900 to 1250 degrees centigrade. Quartz tubes have limited life in the same process. So what we learned today, we learned that why silicon is the most important element in the semiconductor industry. What are its advantages? The main advantages are its abundance, its high temperature adjustment, its band gap, its purity, and its sustainability over longer period of time. So these are the main advantages of silicon. That is why it is used as the basic material, the principal material, the unit material for manufacturing the IC. So in next lecture, we will learn some other fundamentals related with the crystal growth and wafer preparation. This is all for today's lecture. Thank you for listening and watching.